drives. So in EV PMBLDC based EV drive, we require a inverter, a special inverter for driving the PMBLDC motor. PMBLDC motor comes under the special machine category. It comes under the special machine category because it requires a special converter for its operation. Okay. So without inverter, we may not operate this machine. Okay. So this is called a special type of machine. So we supply the current to the windings of the motor through an inverter. Okay, which is also known as voltage source inverter. Okay. So voltage source inverter is having 6 IGBT switches which are connected in 3-phase bridge fashion in 3 legs. Okay. So each leg is consist of 6 switches. One is for upper leg and one is for lower leg. Okay. Both these switches should not be turned on simultaneously. So that is the job of the control. We should always take care that both these switches or IGBT should not be turned on at same time. Otherwise, the DC bus will become short circuited and the inverter will burn away. Voltage source inverter will burn away. Okay. So it has 6 IGBTs: SA1, SA2, SB1, SB2, SC1, and SC2. Okay. So all these 6 IGBT switches have body diodes connected in parallel with the IGBT. Okay. These diodes are freewheeling diodes which are connected in anti-parallel with the IGBT within the IGBT. Means that is not a separate diode. Manufacturer itself connect that diode within that module. Okay. So one module is usually of 2 IGBTs. There are also some modules are available which are having 6 IGBT. Okay. So means complete bridge is also available. IGBT bridge is also available. Even with the gate driver circuit, it is also available. Okay. So at the AC side of this voltage source inverter, PMBLDC motor is connected, and at the DC bus side, a DC bus capacitor and a DC-DC converter is connected at the DC bus side of this inverter. Okay. Now, the DC-DC converter is being fed through a rectifier, okay, which is operating in power factor corrected mode. Means at unity power factor, it's supplying the current at unity power factor. Unity power factor means source side current will be remain sinusoidal, okay, and it will be in phase with the voltage. Okay. So input current, shape of the input current should be sinusoidal and should be in phase with the voltage. Then it is called PFC, power factor corrected rectifier. Now here we find power phase AC source. Okay. So power to this diode will rectify converting this AC power into DC power. So here, am I audible? Am I audible?
Yes, sir. Yes, sir. Fine.
Okay. Okay. So this diode rectifier is converting AC power into DC power. Okay. May you allow me to continue this lecture for 2 hours?
Sir, actually, next speaker will be ready by 4 p.m. Sir, I was unable to hear you.
Hello. Accordingly, I will discuss all the things.
Yes, sir. Please try to finish it by.
Okay. Okay. And please confirm. So this diode bridge rectifier is not having DC filter capacitor in its output. Okay. So we have removed a DC bus filter capacitor from the output of this rectifier. Because of that DC bus capacitor which is connected in the output of diode with rectifier creates a serious power quality issues at the source side because of non-sinusoidal current It demands a highly non-sensitive current from the source. So by removing that capacitor, we may have a very small size capacitor here in the output of this filter rectifier, maybe of the value of 1 microfarad or 0.1 microfarad. Okay, and it should not be more than 1 microfarad at any cost. Okay, so if you want to maintain the power factor correction, means if you want to improve the power quality. So we have removed the DC bus capacitor, and this rectifier is converting AC power into DC power. Now this DC voltage will be full wave rectified voltage. This will not be a perfectly DC bus voltage, because of we are not having DC bus filter capacitor. So we are having the full wave rectified DC bus voltage. That full wave rectified DC bus voltage will be pumped into this DC-DC converter. Okay. So the DC bus voltage is being fed to this DC-DC converter through input inductor LTI. Okay. So this input inductor LTI will maintain the source current constant during the operation. Okay. So what is the advantage with maintaining the continuous input current? The major advantage with maintaining the input current constant is that it will not draw the pulsating current from the source. Okay, so it will improve the stability of the source side. Okay, even means even if you are operating your drive with some weak source, you can maintain that. Okay, but in case of EV, you don't require this. Okay, so actually, if you are operating that PMLDC motor in not using in EV, then you can use this scheme. But if you are using this motor in EV, then you can remove this diode bridge rectifier, and you have to connect this battery. Okay, in place of diode bridge rectifier, you need to connect a directly battery. Okay. So if you are using this PFC scheme, okay, in that case, we will not connect a DC bus capacitor in the output of the rectifier. Okay, we will get full wave rectified voltage. Okay, that full wave rectified voltage will be given to the DC-DC converter as a input voltage. So the input inductor will maintain a constant input current. Okay, so because of this constant input side current, if battery is connected, it will improve the life of the battery. Okay, because it will not draw the pulsating current from the battery. Okay, and it will also not pump the current transient into the battery. Okay, so that will significantly improve the battery life. So if we are having an inductor at the source side, input side in any converter, that helps a lot in improving the stability, overall stability of the source side system. Okay, so if you have a battery, like in EV, you have to have a battery here. You may not have a source in EV. So if you are having a battery at the input side, so it will significantly improve the life of the battery, because of if we are not having the battery, then it will continuously taking the pulsating current from the battery. Okay, so pulsating current sometimes increases the maximum uh, mm, output current of the battery. Okay, so each battery has maximum output current capacity. Okay, so if you will take a pulsating power from the same battery, your current may exceed to the maximum allowable output current of the battery. So so we have placed an inductor at the source side of this converter. Then we are using this CSC converter. Okay, because this converter is especially designed to store more power. Okay, so we have designed this converter in such a way that it will maintain more stored energy in it, so that in case of dynamic operating conditions, so the stored energy in the L and C will be immediately supplied to the motor, so it will avoid the pulsating torque at the motor side. Now an inductor is also connected to the output side of this DC-DC converter. Okay, so that will also further smoothing the DC bus current, and DC link capacitor is also connected. So both of these two, inductor and capacitor, output inductor and output capacitor, will filter out all the ripples in the voltage and current, and it will supply a very stable and constant DC voltage and current to this inverter. Okay, now inverter will control the speed of the PMDLDC motor drive. So how it can control the speed of the PMDLDC motor drive? There are two basic ways. There are two fundamental basic ways. In the first way, what we can do, we can maintain a constant DC bus voltage, and we can switch the IGBTs of the inverter in PWM fashion. Okay, so means each switch will be uh, uh, turn on and turn off thousands of times within a cycle. Okay, so the switching frequency of the IGBTs of the VSI will be very high in that case. That is called PWM switching technique for the speed control of this PMBLDC motor drive. Okay, so second method for the speed control of the PMBLDC motor drive is the controlling the speed of the PMBLDC motor drive through the DC bus voltage. By varying the DC bus voltage, we can control the speed of the PMBLDC motor drive. So here we are using the speed control of PMBLDC motor drive through by wiring the DC bus voltage using this DC-DC converter. So what is the major advantage of using the DC-DC converter for the speed control? That is because of here we are smoothly varying the DC link voltage. So the speed of the PMBLDC motor is directly proportional to the DC bus voltage. Okay, so there is very linear relation between the DC bus voltage and the speed of the motor. Okay, so the speed of the motor will vary in proportional with the DC bus voltage very smoothly. So this is one advantage. Second advantage is the switching frequency of the IGBT switches of voltage source inverter will be very low. Switching frequency of IGBT switches of the voltage source inverter will be very low. All these switches will operate at fundamental switching frequency only. So therefore, the switching losses of all the IGBTs of the VSI will be reduced to a very low value, and the efficiency of the inverter will increase significantly. Now only one switch, SWT, okay, which is used in this DC-DC converter. Now this only in this scheme, only this SWT means the switch which is connected in this DC-DC converter will operate at high frequency only. Okay, all remaining 6 switches of the voltage source inverter will operate at very low frequency. Okay, otherwise, if we control the speed of this PMBLDC motor drive using this inverter only, in that case, what will happen? All the 6 switches, has to be operated at very high frequency in the PWM mode of operation. Okay, so the losses in all 6 switches will be very high, but in this case, the losses will be occur in one switch only, and the losses in the remaining 6 switches will be very less significantly. So the overall switching losses of the IGBT are reduced to a very low level in this scheme. So we are using here the DC bus control for the speed control of the PMBLDC motor drive. So here now I have already explained you that how we are supplying DC power to this DC converter, and how this DC converter, which is supplying an adjustable DC voltage to the DC link of this inverter. This DC converter is supplying an adjustable DC bus voltage to this voltage source inverter in order to get a required variation in the speed of the PMVLDC motor drive. Now, see, the DC bus voltage is denoted by VT naught, and output capacitor is denoted by CT naught. Output inductor is denoted by LLT naught, and the converter side inductor is denoted by LT, and capacitor CT, and switch SWT. So current through the switch is ISW, okay, and voltage across the switch is VSW, and current through the DC-DC converter inductor, that is the ILT1, okay, and while voltage across the VC1 is VCT is CT capacitor is VCT, okay, and input current to this DC-DC converter is ILTI, okay, and the back EMF of the at the terminal of the PMVLDC motor are EMA, EMB, and EMC. Okay, so the back EMF motor back EMF will be of the trapezoidal wave shape, because we are using here PMVLDC motor drive. Okay. So we are having three phases. So three back EMF will be there: EMA, EMB, and EMC, and three stator currents of three-phase PMVLDC motor will be IMA, IMB, and IMC. So the inverter is supplying these three current to this motor. So at a time, two switches will operate. At a time, two switches will operate. One from the upper side and one another from the lower side, lower leg of this inverter. Okay, so in this scheme, the rotor position is detected, okay, using Hall effect position sensors. So Hall effect position sensors are detecting the position of rotor of the PMVLDC motor, okay, in order to commute the current in the winding at the proper point of operation. So the switching voltage and switching current should be as minimum as possible. Okay, so the information about the position uh, will be supplied to the electronic commutation circuitry. Okay, so that electronic commutation circuitry generates the gating pulses for 6 IGBT switches. Okay, accordingly they perform the switching function in order to supply the mandatory current three phases of the PMVLDC motor drive. Okay, so it will be switched from one winding to another, then another to winding, B to C winding, then again to A winding, then B winding, then C winding. Okay, and at a time, two IGBT switches will operate. Okay, so because of here we are using DC bus voltage to vary the speed of the PMVLDC motor drive. So we are taking the DC bus voltage as a reference input. We are taking DC bus voltage as a reference input, and we are comparing this DC bus voltage with a reference voltage. Okay, so this VTO, that is DC bus voltage. Okay, so VTO is proportional to the speed of the motor drive. VTO is proportional to the speed of the motor drive. Okay, so this DC bus voltage compared with the reference voltage. So reference, if we want to change the vary the speed, okay, the PMVLDC motor, then we need to change the reference voltage. We need to change the reference voltage if we want to change the speed of the PMVLDC motor drive. Okay, then the error between these two voltages will be fed to the PI controller. Okay. So the error between the DC bus voltage and reference voltage, that is called error voltage, VE. VE error voltage is supplied to the PI controller, proportional integral controller. Okay. So this PI controller will process the error of the DC bus voltage, and this DC bus voltage error is representing the error in the speed. DC bus voltage error in DC bus voltage is representing the error in the speed. Okay. That means that is a signal of the error in speed only. Okay. So that error signal of the speed is processed through this PI controller. Okay. So we need to set the KP and KI of this PI controller. Okay. And then it will process and it give output as a correction factor. Okay. So the output of this PI controller is fed to the reference current generator circuit that we supply to the reference current generator circuit. Okay. So this reference current generator circuit will also take the source output of the rectifier, okay, as an input variable. If we are using single phase AC source or grid supply for driving this motor, if we are using battery, then we need not to take any feedback from the AC side. Okay. Because of we are taking this feedback in order to maintain the power factor correction. Okay. We are taking the this VRT, okay, as an input variable in order to maintain the power factor correction at the source side, in order to keep the source current sinusoidally, perfectly sinusoidal and in phase with the source voltage. Okay. But if we are not using this AC source at the input side, like in EV drive, we need to replace this rectifier by a battery. So in that case, battery will supply perfectly DC current, okay, and DC voltage. So we need not to take the reference of the battery voltage. Okay. And this input, so this reference current, the reference current generator will take the input from the PI block, and it will take the, optionally, it will also take the input from the output of the rectifier, and it will process these two signals. Accordingly, the signal will be fed to the PWM current controller. So this PWM current controller will generate the PWM pulses, okay, and output of these PWM current control will be the switching pulses, and that will be sent to the gate of the SWT. SWT means that is the IGBT switch, which is connected in the DC-DC converter. Okay. So in this way, we will generate the switching sequence, switching pulses for the IGBT, gate of the IGBT, which is connected to the DC-DC converter. Okay. And as far as the switching signals for this these 6 IGBT switches of VSI is concerned, here we are taking the feedback from the Hall effect position sensor about the positions of the rotor of the PMVLDC motor. Okay, and this information is supplied to the electronic commutation system. Okay, so this electronic commutation system supplying the switching signal to gates of all 6 IGBT switches. Okay, and this inductor is operating in continuous conduction mode of operation. Okay, so DC converter is operating in continuous conduction mode of operation. Okay. The input and output current of the converters are continuous because of the presence of inductor at both the sides, and the presence of inductor makes this system highly suitable for PMVLDC motor drive system for various applications. A single converter is used for both the power factor correction and the speed control of the drive, thus reducing the number of elements in this system. But this is applicable where we are using the grid supply or single phase supply to give power to the system. Okay, and the speed control along with the PFC in this system is achieved via PI controller having speed reference as input. Since the ripple in the output current of the converter is very less, which in turn reduces the torque ripple of the PMBLDC motor drive system, the Hall effect sensor-based electronic commutation of PMBLDC motor drive is implemented in this system at fundamental frequency. This significantly improves the system efficiency achieved by the reducing the switching losses of voltage source inverter. Okay. And the fundamental mode of operation of the PMBLDC motor drive is used in this system. Okay, and that improves the system efficiency. The Hall effect sensor-based position detection system scheme is utilized to extract the rotor's initial position and the signal from Hall effect position sensor fed to the VSI through electronic commutation block to reduce the switching losses. Okay. And that is the setup that we have developed in our laboratory. Okay, for implementation of this scheme. So we are discussing the working of the converter in two mode operation. In mode 1 when switch is on, when mode 2 when switch is off. Okay. So when in mode 1 when switch is on, so a loop current will flow within the inner loop, that is CT, LT and switch, IGBT switch. Okay. So that is shown by the red line. Okay, is it visible to all of you? Am I audible? Am I audible?
Yes, sir, fine.
Okay, okay. So see, when switch is in on condition, okay, the current through this switch will flow. That is, so ISWT is high. Okay, so we are dividing the operation of the system in two mode of operation. In mode 1 when switch is on, in mode 2 when switch is off. So what will happen when switch is 1 is on? The current will flow through the switch, that is ISWT, that is having some value, and then VSWT, because of switch is on, so voltage across the switch will be 0. So no voltage shown here. Okay, in the third trace. In the fourth trace, that is ILT. Okay. So this ILT is current through the inductor which is used in this DC-DC converter. Okay. So it is operating in continuous current mode. Okay. So it is not touching to the 0. Okay. So in on condition, in switch on condition, the current through the inductor will increase. Okay. When it is in off condition, the current through the inductor will reduce and voltage across the switch will increase, and current through the switch will become 0. Voltage across the switch will increase and current through the inductor ILT will decrease, and the capacitor voltage VCT will decrease when switch is on. The capacitor voltage VCT will decrease. Okay, because the inductor will be charged, so voltage across the VCT will decrease, and in off condition the voltage across the VCT will increase, so capacitor will charge when switch will be off, and it will be discharged when switch will be in on condition. Then ILT1 is also increasing. Okay, so ILT1 is the current through the inductor which is used, main inductor which is used in DC-DC converter. So current through this ILT will increase in on condition and it will decrease in off condition. Okay, and the DC bus voltage will decrease in on condition and it will increase in off condition. Okay. So mode 1 and mode 2 both have been explained here. Okay. So in mode 2, the source current will flow through this loop and load side current will flow through this loop. Okay. So the diode will D1 will conduct. Okay. In mode 1, diode D1 will not conduct when switch is on. When switch will be off, the switch SWT will be off, then diode D1 will conduct. Okay, so both the current will flow through this diode. Okay. So these are the Hall sensor positioning, Hall sensor position sensing. Okay. So these waveforms are giving the information about the um, back EMF voltages. Okay, motor back EMF voltages, EMA, EMB, and EMC. EMA, EMB, and EMC. These three are the back EMF voltages of the PMBLDC motor, that is trapezoidal in shape. All these three back EMF are of trapezoidal shape. Okay. That is why this is called as PMBLDC motor. So if this back EMF becomes sinusoidal, then the machine is called PMSM machine. That is only the difference between these two motors. Otherwise, construction is almost similar. Okay, so there's a difference in the distribution of the winding. Okay, so in PMSM motor, that is also permanent magnet motor. Both the motors are permanent magnet DC motors. But in case of PMBLDC, the back EMF shape of the back EMF waveform is trapezoidal, and in case of PMSN, the shape of the back EMF is sinusoidal. Okay, so here the back EMF waveform is uh, trapezoidal. Okay, and that is EMA, EMB, and EMC. Okay, then IMA, IMB, and IMC. IMA, IMB, and IMC. These three are the winding currents. These three are the stator current. These three are the stator current of the PMBLDC motor drive. Okay, so that is stepped in nature. Okay, you can see here it will increase in steps, then it will decrease in similar steps. Okay, so this stator current will increase in a step. Okay, in every step. Okay, and it will decrease after peak value, that will decrease in every step. Okay, so the motor is running 360-degree mode of operation. Okay, so it has 6 modes. Okay, 0 to 60, 60 to 120, 120 to 180, 180 to 240, 240 to 300, and 300 to 360 degree. Okay, so the last waveform is showing the frequency, fundamental switching frequency of the VSI switches. Okay, and these are the uh,
Your voice is not audible. Sir, Jules, sir, we can't hear your voice.
Am I audible?
Yes, sir. Fine.
Sorry, there was call from director office. So sorry. These are the system simulation results in a steady state. Okay. So upper two waveforms are source current and source current voltage. If we are feeding power through the single phase grid source. Okay. So both are perfectly sinusoidal. Okay. So it shows that power factor correction operation has been achieved perfectly, and DC bus voltage is also maintained. Okay. uh, uh, at the constant value. Okay. And uh, fourth and fifth waveforms are the switch voltage and switch current. Okay. Switch voltage and switch current. Okay. And that is also very good, because of switching current is not exceeding to 7 ampere in all the cases. Okay. And switch voltage is also almost peak value of the switch voltage is also 400. That is also very good within the limits. Okay. That is good and within the limits. Okay. So because all these switches, usually all IGBT switches can handle 600, 700 volt very easily. Okay. So at very low cost, such switches are available. So the scheme is very much suitable for them. And last two waveforms shows the current through the inductor DC-DC inductor of the DC-DC converter, and voltage across the capacitor of the DC wave converter. So this performance shows that system is operating in continuous conduction mode. Okay. And this is the system performance under dynamic operating condition. We are increasing the load. Suddenly we have changed the supply voltage. So supply voltage suddenly reduced. So momentarily the DC bus voltage, DC link voltage reduces, but immediately it regains the same DC link voltage, and speed is also maintained the same value. Okay. And grid current is will be increased, because supply voltage is if supply voltage will reduce, the grid current is automatically increased in order to supply the same power to the motor drive. Okay. And then back EMF current, IMA. Okay. And sorry, EMA is the back EMF voltage of the phase A. Okay. And IMA is the stator current. Okay, of A winding. Okay. So similarly, there will be three stator winding current: IMA, IMB, and IMC. Similarly, the three back EMF voltage will be there: EMA, EMB, and EMC. Okay, so this is the dynamic performance of the system under suddenly load change on the motor drive. Okay, so if the load is suddenly changed on the motor drive, what will happen? DC bus voltage will slightly increase, and it will again comes to the its referred value. Okay, immediately. Okay. And load torque is decreased. Okay, here in order to check the system performance in this dynamic operating condition, and the phase currents, stator currents reduce. Definitely that will reduce because of the load is decreased. So if load will decrease, definitely the stator current are supposed to decrease. So they are decreasing here. Okay. And the back EMF voltage, magnitude of back EMF voltage is slightly increasing because of that. Okay. So that is the system performance under dynamic operating condition. So these are the experimental results in steady state. Okay. So that is recorded on the key site DSO. So upper two waveforms are source voltage and source current. Third one is the DC bus voltage, and fourth one is the stator current. Okay. IMA. Only one stator current waveform has been shown here because of the limited number of channels in the DSO. Otherwise, there will be three stator current waveforms. Okay. And these are the switching performance of the IGBT switches. So upper one is the switching current. Okay, switch current. Okay, So the current through the switch. So it shows that there is no disturbance or transient is being appear across the switch during the operation, and lower waveform is voltage across the switch. Okay, so that is also performing very stably, and no transient is appearing across the switch. Okay, and voltage across the switch is also almost 400 volt. That is good and within the limits. Okay, and this is the starting performance, mean dynamic operation of the motor in real time. These are the experimental results. Okay, so the during starting back EMF will be slowly build up. Okay, initially it will zero, then it will build up as shown in the last trace. Okay, lowermost trace. Okay, and the DC bus voltage will increase from 0 to its rated value. Okay, and it will, whenever this grid DC bus voltage will increase, motor speed will increase. When motor speed will increase, it will take more power from the source. So the grid current is also source current is also increasing as we are increasing the DC bus voltage. Okay, so when DC bus voltage will increase, then only the stator current will appear. Okay, and grid voltage is stable. Okay, during starting, so it is not affecting the grid voltage in any way. Okay, so this is the dynamic performance of the system. This is dynamic performance of the system where supply voltage suddenly change and constant DC link voltage. DC link voltage is constant here. So here the grid supply is suddenly changed. So grid supply is reduced to a very low value, means almost half value. Okay, so but because of the variation in the DC AC supply voltage, and there is no effect on the system performance as the DC bus voltage is restored to its original value very shortly. Okay, so this result shows that the dynamic performance of the scheme is excellent. Okay, as the DC bus voltage is restored immediately, means it will not affect the speed of the motor drive. So any change in the source side voltage will not affect the speed of the speed performance of the DC motor drive, because of DC bus voltage has been restored immediately, and this DC voltage is representing the speed of the human DC motor drive. As long as this DC bus voltage is constant, maintained constant, means regulated, means the speed of the motor will also be regulated and will remain constant. So in this case, here we are increasing the DC reference voltage. Okay, so the DC reference is changed. Okay, so DC reference is increased in order to achieve the higher speed of the drive. So when we increase the DC link reference voltage, okay, so the output voltage, sorry, the uh, VTO, okay, output DC link voltage will increase. Okay, so here we see that if we'll increase this DC link voltage accordingly, so all the system parameters will be changed in order to accommodate this DC link reference voltage, and the motor will reach to the new speed value in accordance with the new reference voltage of the DC bus. Okay, and this is a system dynamic performance in experimental mode for a sudden load change in motor. Okay, so here the load is increased. Okay, but with increase in load, we can observe that DC link voltage is still maintained constant. Okay, so the any sudden change in the load is not affecting the drive performance here. Okay, and these are the power quality performances. Okay, so this is valid here because we are presenting the result for the grid connected system also. So you can see here the power factor is unity. Okay, power factor is unity, and THD is 3.6%, that is less than 5%, is meeting the IEEE 519 standards of the power quality. Okay, and the THD at 230 volt supply and THD at 90 volt supply. In both the cases, see, at very high voltage and at very low voltage, in both the cases, THD 3.6%, 2.4% respectively, both are the less than 5%. So in the whole range of operation of the speed control of the motor, the system is having very high power quality and having less than 5% THD in the source current. And this is the comparison with the existing topology. Okay. Thank you. So now the session. Okay. Let me discuss some aspects also. So here, see, when we implement this scheme in real time on DSP controller, so in DSP controller, we have to decide the ADC channels. Okay. So whatever the input signals you have, the number of ADC channel of the DSP controller should be equal to or more than that. If suppose in my this control algorithm, if I'm taking 5 input variable, means like the DC bus voltage is input variable here. Okay, source current is one input variable. Okay, so for the DC bus side control, we are having 3 input variables: source current, source voltage, and DC bus voltage. Okay, so we have 3 input variable. So we require a DSP controller which will having 3 ADC channels. So information about these 3 variable will be supplied to the DSP control through 3 ADC channels. Okay, and we have Hall effect sensors. Okay, so we are taking the input from the Hall effect sensor. So 6 ADC channels will be further required. Okay, so the total requirement of the ADC channel of the DSP controller will depends on the total number of input signals or input variable signals. Okay. Okay, so the number of ADC channel will greatly affect the cost of the controller. Okay, then output of this DSP controller will take the values of the input variable in every sampling time. So we'll set one sampling time. Suppose we have set the sampling time of 40 microseconds. So after every 40 microseconds, my controller will take the instantaneous value of these quantity, okay, as an input. Okay, after every 40 microsecond, and it will supply to the algorithm. Okay, and to the DSP controller. Then the DSP controller will execute the control algorithm. Okay, and it must be able to execute the algorithm before 40 microseconds. Okay, means maybe in 36 microseconds, 37 or 38. If it will fail to execute the algorithm within the 40 microseconds, then it will start malfunctioning. Okay, so in that case, you have to increase the sampling time of the converter. But if you will increase the sampling time, then what will happen? The resolution of the control will become poor. Okay, so in order to improve the resolution of the control, what we should do, the sampling time should be as minimum as possible. So there are 2 ways to achieve this. Either you purchase a controller of with high mathematical calculation capability, so that will increase the cost of your system. Okay, another way, you can reduce the calculation burden of your algorithm. Okay, mathematical calculation burden of your control algorithm. So the calculation requirement will be reduced. So the same controller can be operated with lower sampling time, and so you can enjoy the better resolution of the control. Okay. And the output of the DSP controller is fed to the IGBT switches through the optocoupler switches. Okay, so we use optical isolation between the output of the between the power switches and the controller side. Okay, so if there is any fault occur at the power converter side in the switches, so that should not be transferred to the controller side. Okay, so That's all about this scheme. Okay. So now the session is open for the query if you have any. Am I audible?
Yes, sir.
Yeah, yeah. So any query if you have, or not only regarding this, you may ask any question related to power quality, power converters, or inverters, or implementation of any scheme using analog control, DSP control, whatever query you have, you may ask.
Participants, please send your queries.
I think there is no query.
Yes, sir. I think so.
Okay, this lecture is good.
Yes, yes. Fine.
Okay, okay. So thank you. Your good name, I not asked you. Actually.
Myself, Anupam Agarwal.
Anupam?
Agarwal.
Okay, so thank you, Anupam. Okay, and thank you, Professor Manmohan Garg sir. So thank you for giving me opportunity to deliver here. So may I leave now?
Yes, sir. Please, your choice.
Thank you. Thank you.
Thank you, sir.